Hello, my name is Pratyush, and today we'll be solving the 2026 AP Physics C Electricity and Magnetism FRQs. So let's get started with the first one. So the first one tells us that two very long cylindrical current-carrying wires S and T are oriented parallel to the y-axis, as shown in Figure 1. The centers of the wires are in the xy plane. The wires are described as follows. Wire S has radius 2a and is centered at x equals 0. Wire S is non-uniform current density and carries a total current I naught in the positive y direction. The magnitude of the current density in wire S as a function of the radial distance r from the center of the wire is described by J equals CR, where C equals a positive constant. So we can already see that we're dealing with non-uniform current densities, which kind of tells us that we might need to use some integration. And then the second point tells us that wire T has radius A and is centered at x equals 10a. Wire T has non-uniform current density and carries a total current of I naught in the negative y direction. So we can already see that both wires are carrying the same magnitude of current, but in opposite directions. So let's see how that plays out. So here we can see both the wires and along the x-axis. So part A asks us, point P is located inside of wire S at horizontal position x equals A. Derive an expression for the magnitude of the magnetic field at point P due to only the current in wire S in terms of C, A, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay, so it's asking us to derive the magnetic field as related to a current in a wire. So that kind of already tells us that we need to use Ampere's law. So we'll probably write that down as our fundamental physics equation. So let's write that down. So Ampere's law is the surface integral of BDL equals mu naught I enclosed. And here we actually know everything. Here B is what we're trying to find. We know DL and mu naught is a constant. Here we just need to find the enclosed current at point P within wire S. So as I mentioned before, here because the current density is non-uniform, we do need to integrate. So to get I enclosed, we have I enclosed equals the integral of J dA, and area is pi r squared. So then dA equals 2 pi r dr. So then we have I enclosed equals the integral from, and our bounds are going to be from 0 to a because it tells us that point P is at position A. So 0 to a, we'll put J and we'll substitute this in for dA times 2 pi r dr, and the problem actually gives us an expression for J. So we get I enclosed equals integral from 0 to a of CR times 2 pi r dr. We can take all the constants out of the integral. We get 2 pi c times the integral from 0 to a of r squared dr. Take the antiderivative of this. You have r cubed over 3 from 0 to a. And then this gives us, if you solve for this, you get 2 pi c a cubed over 3. So this is going to be our enclosed current. But we're not done. We need to plug this back into Ampere's law. So then we have the integral of B dl equals mu naught times the enclosed current, which is going to be 2 pi c a cubed over 3. BDL, because the magnetic field is going to be constant, and we can take that out of the integral, and DL is just going to be 2 pi is just going to be 2 pi a. So then we can do B times 2 pi a equals mu naught 2 pi c a cubed over 3. And essentially, if we simplify this down, we get B equals mu naught C A squared over 3. So this is going to be the expression of our magnetic field for part AI. So now let's do part A2. So it says on the axis shown in figure 2, sketch a graph of the magnitude B of the magnetic field due to the currents in both wires as a function of x along the x-axis in the region 2a to 9a. Sketches made in the shaded region will not be graded. Okay, so it says as a function of x along the x-axis. So from 2a to 9a. So 2a to 9a is in between both the wires. So in between both the wires, we can derive the magnetic field in between both wires also using Ampere's law. And this is a pretty known result. So around a wire, the magnetic field is going to be mu naught I enclosed, but in this case, the enclosed current is I naught for both wires. So you get B times 2 pi R, where R is how far away you are from the wires, mu naught I naught. And then you get B equals mu naught I naught over 2 pi R. So this is the expression for the magnetic field a distance R away from one of these wires. But using the right-hand rule, we can tell that in between the wires, the magnetic field points in the same direction into the page. So that means the magnetic field adds up. So we have an expression for the magnetic field in between both wires is going to be mu naught I naught over 2 pi x, where x is your position, plus mu naught I naught over 2 pi times 10a minus x. And the reason for this is because, so this gives you, at a position x, this gives you, this part gives you the magnetic field from due to the current in wire S, and this part gives you the magnetic field due to the current in wire T. So because wire S starts at 0, the distance between where we are and where wire S is just going to be x minus 0, which is just equal to x. And then the distance between wire T and where we are in between them is just going to be 10a minus x. So that's where we get this expression from. And essentially, if we were to graph this expression, it would look somewhat like this. So it would be, and I'll put 5a here. So starting from here, it would be kind of concave down, starting from 2a, and it would reach a minimum at 5a, right? And then it would start to, sorry, I should have probably draw this a bit closer, equally spaced. And after it reaches a minimum at 5a, it'll start to go up towards 9a. So it's kind of a U-shaped graph that reaches a minimum at the bottom. So that's what this is going to look like. So now let's take a look at part B. So part B tells us that at the instant shown in figure 3, a small sphere with charge q is at horizontal position x equals 5a, and moving in the xy plane with speed v in the positive x direction. At this instant, the net magnetic force exerted on the sphere due to the currents in wire S and T has magnitude F. Derive an expression for F in terms of A, Q, I naught, V, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Okay, so we know that the force on a moving particle is going to be equal to Q, V, B. Okay, so what we know Q, it gives us Q, and we know V, it gives us V. So what we need to find is the net B field in between the wires. And we kind of already did that when solving the previous problem. We got that the net B field in between both wires is going to be equal to mu naught I naught over And we kind of got that on the other side here. We got, it's going to be mu naught I naught over 2 pi x over 2 pi x, where x is how far you are from the origin, 0, plus mu naught I naught over 2 pi 10a minus x. And it tells us that it wants the force at the instant the particle is at 5a, is at x equals 5a. It tells us that. So we can plug in that position into this expression to give us the net B field experienced by that particle at that position. So let's plug it in. We get equals mu naught I naught over 2 pi times 5a plus mu naught I naught over 2 pi times 10a minus 5a. This is going to be equal to mu naught I naught over 10 pi a plus mu naught I naught over 10 pi a. And this is just going to be equal to mu naught I naught over 5a. Okay, so this is going to be the net B field in between both wires at this position, at the position x equals 5a. So we can just plug this directly back into our force expression that we got earlier. So we get the force equals, we'll plug in the magnitude of the charge that they gave, so they want us to use capital Q. We get Q mu naught I naught times V over 5a. So this is going to be your final answer for part B, and that is it for question 1.